Sorry for being before lunch. I hope no one sleeps. And how many of you are students here? You can raise your hand. And how many are from industry? And how many are from something else? I'm curious about what's this something else. Oh, maybe I don't know. Yeah. Anyway, so I'll be talking about how we saved 50 terabytes of memory. It's not disk memory, RAM memory in Workday. And how many of you knows Workday? Yeah, not many. I need to explain that. Yeah, I didn't know before joining Workday anyway. But yeah, Workday is one of these top 500 SP500 companies. In the group of the 500 biggest companies in US, and like close to 80% of SP500 companies are using Workday software for like all the HR software. If you're ever interviewed for an US company, or even Europe as well, the market here, a bunch of companies are using Workday. You probably had to fill some forms to like during this interview process, or if you worked in any big tech, you probably have used this system. So all your HR information, finance information, your payslip, all this stuff is in Workday. It's the biggest one nowadays. The best, like some competitors are SAP, SAP, and Oracle. Yeah, Workday is in this field. And a little bit of how I'll get there to explain this journey about this 50 terabytes of memory saved. I'll talk about like how we built foundation 2 years ago when I joined Workday to help the team to achieve that, and like some challenges we faced with license and cloud cost. I think many people, many teams face the same challenge. How we applied science and research to figure out what could be saved and how we could save that, and the solution that we did. I will reveal the details, and yeah, all the results, performance gains, and etc. etc. So the Kato approach. Many of you, I think, heard about the Kato versus Pet story. Like in the past, we had, like the previous presentation, he talked a little bit about that. We had servers that had a name. My first company, when I worked in Brazil for the government, like this electoral system, we had like servers that had a name of TV series like Dexter or Friends or whatever. Like we put like beer names, we put like specific names on the servers because we knew them by name. Like the mail server had a name, the database had another name. We knew specifically how to jump in the server via SSH, and it is a very pet approach. And like when we go to like very high scale, like petabytes of data to manage, you don't want to work like that because you cannot manage like thousands of servers by name. So we need to go more Kato. Like servers need to be disposable. I can drop a server and put a new server there. I know it's not a good approach thinking about animals, but like, yeah, that's what the IT world coined this term. And yeah, our pet approach were like this. We had petabytes of data to store. We have about 2-3 petabytes of data just in logs. I'm from observability team. So every single transaction we are doing, our support team have a very low SLA, like to support the customers. And if you are not getting paid because Workday is down, you get a bit annoyed. Like big companies like Walmart or like Accenture, like if they have a failure in Workday, it's a big problem. And we have big number in dollars contract that if we don't reply in X amount of minutes, we are in trouble. And my team needs to bring all this visibility of all of this data and have one single log system for the whole company. And it's on petabytes of data. And to scan that in disks, it's something insane to think about. Like how do you reply that in 2 seconds? Any query, like any aggregation in 2 seconds. And yeah, trillions of lines. We grow about 5% per month. If you do the calculations, it's like every 1.5 years we double size in logs. And you have like just machines producing these logs, like more than 250K. Yeah. And like if you look at this graph, our application was more like every ingester, because we started with this server called ES in a Kubernetes namespace called ES, and it's an Elasticsearch server. Initially, this grew to, like, we were growing vertically, the servers. Then we start to grow horizontally. Like, imagine 10, 15 years ago when Workday started, like, Elastic was there, and you, like, put the first server. No, it's not enough. Let's put another one. Oh, let's put more. Let's put more. Like, but there is a limit, because the way that Elastic was designed many, many years ago, when we had just data centers, not cloud, it was thinking about shards, replication, and thinking about like having these master nodes and the leader. You have a leader election, and only one node is the master of this communication. If you write any log and it closes some segment and closes some shard, it needs to talk to the master to say, hey, my information is in this host and the replica is in this other host. At some point, this master becomes a bottleneck, and you cannot put more than 200 nodes. And if you put more than 200 nodes in your cluster, you need to do a lot of tweaks to achieve that. And you don't want to do a lot of tweaks when you're thinking cattle here. And then we go vertical, and you start to buy bigger machines and bigger machines in these 200 nodes in AWS. But at some point, it's getting too expensive. I want to use any machine. And if you get bigger machine, you need to reserve instance, you need to do a lot of work. That is complicated. And then the next idea is like, let's put another cluster. Yes, 2, Elasticsearch 2. The problem is the first cluster has much more data than the second one. And you need to tell all your ingestors to ingest data and your load balancer rules, just the previous data from the first clusters to the trust customers, to the server 1, the yes, and the other customers to the yes2, the new customers. And at some point, the yes2 become so big that you need to put yes3. And you have a lot of cattles, but a lot of pets, sorry, but like at cluster size. And that's a problem again. And you're like, yeah, how to solve this? And then myself and the team, we re-architected the system. Say, no, we want everything is a cattle here, even the cluster is a cattle. So all our common logs, we changed that. I created some load balancer smart rules and some health check mechanisms that can score every cluster according to CPU, memory, like if it has more room to receive ingestion and things like that, or the query performance. And then like we score from 0 to 100, and we send more data or less data to this cluster if it depending on the health. And instead of thinking nodes, we started to think clusters. And we made that easy enough in the naming conventions and the way we organize namespace and everything inside Kubernetes to like just put a new cluster inside one specific group. We split that also in domains, in groups. Like these 3 clusters you initially saw that. We split that like, oh, this will be called group 1. But if another team, an infra team that has nothing to do with customer stuff that can break our general cluster, we just create a group 2 there for these guys. And we route specifically to group 2 in our load balancer. We don't create like crazy rules, like putting my customers to know where to route things to. Now my customers doesn't know anymore like where to route things to. My load balancer has all the intelligence and everything written in code, where telling like which cluster I should send my information. So I can put infra stuff in one group. That's a group of many clusters with 200 nodes. And I can put like just normal customers from Workday logs in these other groups. But from the customer point of view, whoever is using the system, they have the same view. They can access the same information in the same screen, Elasticsearch, doing federated search in all of these more than 30 clusters. That looks more like a Kato approach. But like even doing all of that, I was able to now manipulate machine size the way I wanted, like get any commodity hardware. Like if I find that something is cheaper, put it in GP3, or if it's cheaper, put in local disk, whatever, I can just swap things quickly. But like at some point we hit like the license cost implications, because if you get more cores, Elastic will come to you and say, hey, yeah. Or if you get more memory, yeah, you need to increase your license price. And also, the cost in AWS, like this growing 5% every year, every month, and doubling size every year, is not being sustainable. And we were trying to find some solution for that. In the middle of this discovery, I found that we had a big problem with, let me just check my time, yeah, 10 minutes now. We had a big problem with the I/O, and I'll show a bit more of details about that, but like we found that, hey, looks that we are 100% CPU all the time, but we are not really 100% CPU because of CPU. It looks like something else is wrong here, and then when I went to do my benchmarks, I found that we were mostly on I/O wait state. If you are familiar with Linux, like when you look at your just CPU utilization, sometimes you can be 100%, but when you look at the load and other parameters, you see that that's not just because the CPU is being utilized. Utilization is divided in many points, like the system, the kernel, or the interruptions. If you are doing like network and I/O or I/O wait, in the wait state, that can be I/O, can be network. You are most of the time doing I/O wait. And I was like, yeah, it seems that we didn't pick the right technology here to build in behind the scenes. And we are paying a lot for CPU and for memory to try to save us from some I/O problem. And at the same time, Elastic wanted us to reduce 43% in our memory footprint. Otherwise, like, we would pay like a few $1 million to just for the license, to keep the license. And to avoid this penalty, I got a project in 3 months to, like, how do you save 43% of memory footprint without breaking customer performance? I'm like, yeah, nice challenge. And we had 3 months to deploy that, to like prove the point and try to analyze what was wrong in the system. No, I tried to bring, all my background was in, when I did my master's degree back in Brazil, it was trying to analyze performance between the SSDs, HDDs, memory, inside the kernel, using perf and system tap and a bunch of low-level stuff to understand how this interaction between these guys and using hybrid storage could work. And I was like, okay, I'm going to apply this science here. And I used Feel, that was a benchmark tool designed by the Linux kernel maintainer, to test if they make a change in a block storage layer, anything in the block storage layer, if that's impacting or not. It's give you a lot of details on how your I/O path. I use ES Rally to do macro benchmark, like micro benchmark, to understand where is my pain point, like if I get a single machine, a single box, what's going on. And the macro benchmark to check like how my ingestion, if I try to ingest data, is going. And we have basically these two methods, how my ingestion is going, if I can ingest at the rate that I need to have my log in my SLA inside the system, and also my query. I need to reply in X amount of seconds every single query. And then I did my macro benchmark, but there is no tool to do that, especially at this scale. How can you test a 3 petabyte system? I could not ask my manager, hey, let's replicate that, because I need a test environment of 3 petabyte. That's like millions. And I couldn't ask that for a month or 15 days, and it would take like many days to copy this data to test with some real data. And that's the picture I showed before. I tested that with you, and I found that EBS in AWS caps you at 3K IOPS, and that's the basic one. If you want to get more, you need to pay for IO1, IO2, that's another type of IO, but you pay a lot just to get IO1, IO2, and that's like 16K. But if you get local disks, in AWS itself, like you get 219K, 300K of IOPS, which is quite different depending on your application. And our application is an IO-intensive application. I was like, well, it looks like a design mistake from the past. I know that at the time when the team moved from like data center to the cloud, they had not much time to think about that. But like looking backwards, like, whoa, if we knew that before, we never put that our data in a EBS. But that's the normal move. Everyone goes to EBS because we have replication, you have a bunch of stuff that you can just plug in, plug out to your system. So the high CPU was a lie, as I said before, and the process was just waiting for storage all the time. And we put a lot of memory to compensate the lack of disk throughput and latency. And another problem here, EBS is on the network. If you need to leave your machine and to go to the other machine and you do a lot of IOPS, you accumulate this latency and like speed of light. You cannot fight against that. And it's like 20 centimeters is 1 nanosecond, more or less. And like to go to the other data center or to go to the other rack to get your data and return with 4 kilobytes, that's a block, that's a lot of time if you sum all of that. And that's what we call trashing. You keep more time going and returning, and your CPU waiting for that than doing your real job and processing your stuff. So this would help a lot on that, and we were looking for the wrong metrics to fix that. And this was me testing with one CPU, 2 CPUs, one thread, 2 threads, 4 threads, and until 64 threads. And you see, EBS just caps you for read and for write, and for random read, random write, doesn't matter. It just caps you at 3K. And then I started the macro benchmark. Like, okay, I understood in one box. And then I got 1K I got like 1K size of the whole cluster. I could build like some terabytes cluster, but like very small scale, but that in a way that I could reproduce the petabyte scale theoretically, that I could like just calculate the proportions of what I'm doing if I can apply to the petabyte again. And I got some equivalent data set to try to run my queries against it and try to ingest the data. And I tried, like, I made a spreadsheet and got all the different local disk machines from AWS and tried to run benchmarks on that to figure out what's the right hardware to run this architecture, this application, to pay less at the end of the day. And I found that our benchmark result was 123K logs ingested in this single machine. That was the best one in the benchmarks at P99. And our peaks in our normal system was 40K. It's like, okay, this machine looks good. I can put almost 3x here, or 3x less than what I need. So I can put less hot nodes to ingest. And yeah, and also we took the opportunity to change to ARM computing. Like I think everyone is changing to that because they are less expensive, more green, I'd say, as well. And then I run, that's the most complicated one. There is no benchmark tool, even from Elasticsearch. It's a very billionaire company. To figure out at this scale, we are one of the biggest customers in the globe. We were, I think, the biggest one running Elasticsearch for a while. And they don't give you a tool to run at this scale a benchmark of your queries. Then we built internally an auditing system that collects the slow logs, joins that with the auditing logs from Elastic Security Logs, and we figured out exactly which customer at which time run which query, like the query details, and what was the latency in every shard. And I got all these statistic metrics from this, and I could like reproduce running in this proportionally small cluster that I built, and I found this graph. Like I could compare the queries from EBS versus queries from local disk. That was the best one in my test. But there is something weird here at the end of the test. Like this is the horizontal, here is the axis, the query ID, but they are sorted by the execution time in seconds. Turns out that if I put that in log scale, I see that at some point the local disk is crossing the EBS here. And the point that it's crossing is about 1 second. But wait, my SLA is 1 minute for the query. I was like, okay, I don't care if this query is slow from this point on. So I don't care if EBS is winning because they have a lot of memory for all of these queries. I care about these slow queries here. So let's explode that a little bit more. So I excluded the bad queries there. And got queries only above 1 second. And when I look queries above 1 second, the local disk is winning for everything. So you see the difference here. This graph doesn't tell you anything. When you start to explode, change scale, think about what's your SLA, think about like what you really care. This guy was beaten by 53%, like every single one, and it was better in 92% of the queries. So at the end of the day, we care about P95. We don't care about if one user is running a bad query, a very slow query, because the query is bad, like it's doing a lot of aggregation that shouldn't be doing. We care about P95. And in P95, this new architecture that was 50% cheaper and with less memory to the environment and CPU and everything was better, like in queries, 9x better like in the performance for your queries in terms of latency. And this is like, if I get just above 1 second, the P95, you see the amount of queries that local disk is above. If I invert this graph and filter by local disk doing the cross check, the local disk will be still being part of this side, and being much better than ABS. So in the solution, we basically, for this migration, we used like OpenEBS that helped a lot. OpenEBS is a technology that you can use in Kubernetes, that you can create drivers inside Kubernetes that you say like, hey, it's very complex to plug local disk from AWS inside your Kubernetes cluster. But unless you put a bunch of scripts, a bunch of things, but OpenEBS just facilitates that, and we use some other driver inside OpenEBS to create LVM. So I can just get one, like for the hot machines, I could put a bunch of small machines connecting to LVs inside LVM, and everything looked like GP3 at the end of the day. We made like the operational very simple. Like I did the migration, the rest of the team didn't notice that because it's just a driver. I had to work to implement this driver and to make that smooth to the team. But we are running on local disk machines, but no one noticed that. It's just normal thing. And yeah, we did that with OpenEBS. We used the elastic replication, like I changed like half of the replicas all to the local disk, just changing the driver. And we got elastic copying this data over the AZs. And also we did S3 snapshots of everything. S3 is quite cheap. For that, to ensure that if anything breaks in the middle of migration, I can just restore these snapshots and everything is saved. So this is the same picture, just in a different way. How we did this preparation, move the data to the shards replicas, and we did the code cover after that. And this is just for a picture, is how we put the design to get the OpenEBS and LVMs and the EKS bootstrap scripts to make it work together. Performance gains, as I mentioned before, we dropped the ERUs, that elastic resource units for the license by 48%. We didn't pay the penalty to Elastic. They were not much happy. And yeah, the user was like, what happened to the system? Now it's like 9x faster than what it was before. And the company was paying average 38% less to AWS on the bill at the end of the month. It was millions for the company. And like the migration was 0 downtime at the end of the day. If you have any question, please.